We are at the top of the hour, and I guess it's time to start. So, if the audience has any opinions on this kind of marketing, keep it coming. You can use the chat board or Q&A board or whatever we have in Zoom. I have no idea, but Jerry, are you there? Should we kick things off?
Absolutely, yeah. I'm ready to get this ball rolling. This is going to be a good topic.
All right. So just FYI, this webinar will be recorded and you will receive the link from our friendly folks at marketing in the coming days to your email. So if you'd rather go out and enjoy the sunshine, by all means, the webinar recording will be all yours. Don't leave though. Just don't. Anyway, today, Jerry, you're the one that kind of started this. Today we'll be using Zoom.us, and it's really yours and Joel's fault, isn't it? So we have used the webinar before, right?
That's right. Yeah, I'll take the blame for it if things fall off the rails too much on the technology side. But yeah, we're hoping this will be an improvement, if anything, from audio quality to video. So if you have any issues or anything like that, definitely make sure to utilize the chat function or the Q&A function and let us know. But yeah, hopefully this will just greatly enhance your overall experience.
And to celebrate that, I have gotten a brand new Blue Yeti mic as well. So we'll see how it goes. Any comments on the audio quality, like Jerry said, video quality, anything, let us know. Yeah, this is actually a screenshot from GoToWebinar, but I'm assuming Zoom also has this QA functionality as well as a chat functionality. Does it have both, or are they kind of integrated, or how does this work? Literally, I opened Zoom for the first time like 2 minutes ago.
That's how we do things around here. Yeah, really similar functionality if you've joined any of our previous webinars before. So your lines are obviously muted, and then you have the Q&A box there to locate. We also have the chat enabled to be able to speak directly with the panelists. So feel free to leverage those. But yeah, the Q&A I'll be monitoring throughout the session here, myself and UC, and try to get those questions answered for you quickly.
Great. So today our main presenter is Dr. Hintersteiner. You have an intro slide about yourself later, or you want to say a couple of words now? You seem to be in whatever that means.
I do have an intro slide a little later. But yeah, I'm CWNE number 171. I've been very active in the CWNP community, which is how I know UC and Jerry and a whole bunch of other folks at EKAHAU. And I'm really looking forward to doing this webinar today.
Thank you so much, Jason, for doing it. It's a pleasure, and this has been a long time coming. So glad to finally find time from your and our schedules to make this happen. My name is Jussi. I do marketing stuff, product stuff, everything kind of stuff here at EKAHAU. Actually, today I ruined our new $3,000 coffee machine. So that seems to be one of those janitorial duties. Who's this guy then?
Hey, this is Jeriola, CWNE number 238. Yeah, I am the product knight here at EKAHAU, at least according to our marketing department that did a fantastic job with their photoshopping skills.
Yeah, knight in a semi-shiny armor.
It's battle tested, right? That's what we do on the product side here. We got to battle test some things, so it's fitting.
It's no beta, man. And for those of you who came here for the actual content, this is what Jason is planning to talk about, and we'll give controls to Jason in a second. Before that, the mandatory. We have a really extensive training program. We're doing 150 trainings this year, and it's taught by the industry's very best, including Keith Parsons and some of these other guys you may or may not have heard of. Please go to ekahau.com/training for more information. The training is also available in Spanish, French, and German. Anyway, this is something we launched recently with Aruba at the WLPC conference. It's Bluetooth coverage heat map, so it allows you, ESS upcoming 9.2 release will allow you to plan for Bluetooth coverage as well. So it includes AP integrated BLE as well as BLE beacon placement, and allows you to simply, design BLE systems that provide high location accuracy. Now, this is big news for us at EKAHAU, but small news for anybody else. So this is our new Helsinki office. This is what it looked like a day or two ago, and now it's starting to look a bit better by the day. Then in case since you're here, you might be an EKAHAU customer, and thus you might be interested in EKAHAU products as well. I'm just going to show a really quick demo of an upcoming feature from the EKAHAU tool, and this is what we already demoed briefly at, I think, Cisco Live at least. So one of the features is called Cell Edge, which essentially means that I have brought in a floor plan from a CAD file, which includes walls and all that kind of stuff, and then I'm about to place an AP. So instead of having to wait for the signal strength coverage to update, I don't know, Jerry, how quickly does this update to you? But the idea is that, sorry?
Yeah, it's looking pretty smooth on my end. Hopefully it's coming across accurately or real time for everybody else. But yeah, it's pretty instantaneous looking.
So what would you, Jerry, use this for?
Well, I think for kind of a speed planning, right? So this is on the predictive modeling side of things, and if we need to define for a certain boundary of signal, and that's a primary criteria that we're designing for. I think this is going to be really useful for our customers. And this is obviously something based off of directly feedback in the feature request that we receive. It's something for this kind of quick planning capability, so you can visualize the boundary or edge of the cell, and then be able to make sure you have adequate overlap, but also make sure you don't leave any corner gaps, right, in like the corners of the building, like you're doing there.
Exactly. And should this be called Cell Edge or something else? That we're still debating. We still have like a week to the product release, so we can still make changes, right?
Yeah, nothing set in stone. So we're taking feedback on what this feature should be titled as. So we'll see what we end up with.
Excellent. So that's just one of the things upcoming in the June release. So this should be out, yeah, I don't know, week or two or something. Jerry, do you know the schedule? I mean, something like that, right?
Tomorrow, next week, something like that. Yeah, it's coming up pretty quickly here. So we're, finalizing some of those details, putting all the, putting the QA through its paces here. But yeah, in the coming weeks, right? So we're going to be pushing this new 9.2 update pretty soon.
Excellent. And then we have another pretty cool feature, which we will have in experimental mode first, so that we learn more out of it. And we've used these experimental features before. For example, the height of the client device we should propagate the signals for. So typically, if you press Control and go to visualization options, you can choose the visualization height. So this has been there for a long time as an experimental feature. So if you have forklifts which have PCs at 10 meters height, that's what you can do. But that's old news. The new news, however, Jerry, what has been missing from our spectrum analysis functionality?
I don't know. It doesn't make me any coffee. Now, one of the number
right on the money, sir. Yeah. That's why we hired you, to give accurate CWNE level answers, right?
That's right. Very technical answer, right? No, one of the biggest, as soon as the Sidekick came out, right, one of the big requests that started coming in right away very frequently was around, all right, what is this interference? Now we have this great visibility into the RF environment, right? We can see that there's something out there that's not Wi-Fi, but, it leaves me questioning, what is this energy that's being detected now by the Sidekick? So yeah, you want to talk about what you're showing here?
I guess it's pretty self-explanatory, and so it automatically detects the interferers or some of them, and we want to grow the database together with the community of the classifiers or interferers. But the idea is indeed that I'm actually glad I'm on 5 gigahertz, because otherwise I hope you guys can still hear me. And this happened in a previous webinar where I killed my Wi-Fi I was on. So yeah, that's kind of what it does, and we want to grow this feature with you. And to enable it in 9.2, you essentially right-click on the Sidekick icon here, and then you say enable the experimental interference detection. So again, right click here, enable interference detection, and then in the full screen RTFM, you would go from no interference to show interference. That's how it works. It won't save stuff on the map, but it will give you a feel for the feature on how it works today. And it won't show anything on the map yet. I don't know, it might be coming, who knows? I'm not allowed to talk about the roadmap. And actually I already did for the last 5 minutes. So, and Mikko is now showing thumbs up and love, so he approved. Okay, so anyway, that's it from our side. Just a couple of features. Let us know what you think on the QA or chat board or anywhere as we switch to Jason. What do you guys think of the upcoming features? And with that, Mr. Hintersteiner. Or unless there's anything more for Jerry to show, we're ready to the main star of the show.
I think we stole the show enough. We can pass the ball over to the main point of this webinar, right? So yeah, Jason, are you ready to share your screen?
Yeah, let me see if I can share my screen and flip over. So
Kick me out, man. Kick me out.
Give me a second. So can you guys see the presentation?
We can.
Excellent.
Plus, we can hear your pleasant voice, Jason.
Excellent. So first, I want to thank EKAHAU for the opportunity to present on Mesh. It's an honor to be here with all of you. And to shake it up and make this topic a little more interesting, given the presentation Hamlet Shakespearean theme, which will become kind of readily evident. No, I am not an expert in Shakespeare, and I am not a member of the Royal Shakespeare Company, but I will do my best. But I certainly know quite a bit about Mesh, which is the main topic of today's presentation. I'm the Director of Business Development at LigoWave Networks, and if you have questions about LigoWave, please ask them at the end. So, to mesh or not to mesh? That is the question. And I'm going to start with a Hamlet quote on Mesh. To mesh or not to mesh, that is the question. Whether 'tis nobler in the mind to suffer the slings and arrows of tangled Ethernet, or to take arms against a sea of RF, and by opposing end them, to die, to sleep, to transmit no more, and by a sleep, to say we end the RF interference, and the thousands of dollars running cable is heir to. 'Tis a communication devoutly to be wished. To die, to sleep perchance to dream of flowing wireless frames. Aye, there's the rub. For in that omission of wires, what data traffic may come? When Ethernet has shuffled off this mortal coil, Mesh gives us pause. So let me start the presentation telling you a little bit about the Bard, myself. I am CWNE number 171. I'm not going to focus on all of my credentials, but I will talk about my background in Mesh. Because I am a seasoned veteran in Mesh. When I got into this field in 2008, 2 weeks into my first job in Wi-Fi networking, I was sent to a Mesh network in Sugar Grove, West Virginia, in order to debug a Mesh network that my company had deployed there that wasn't working properly. And for anybody who doesn't know where Sugar Grove, West Virginia is, you go smack dab to the middle of nowhere and then hang a left. That's where it is. In the end, of course, it turned out to be an object lesson in self-interference because there was a lot of traffic and everything was on the same channel. And the more traffic you had, the more people trying to use it, the worse the mesh performed. And we'll get into a little bit as to why that happens a little bit later in the presentation. I've also designed, deployed, and troubleshot dozens of mesh networks and mesh deployments over the last 10 years, both in my role working for service providers and then later in my roles in working for AP manufacturers. So I unfortunately know quite a lot about Mesh. My current role is the Prince of Business Development, actually Director of Business Development at LigoWave Networks in Canton, Georgia. And I will state that all of our Wi-Fi access points do support Mesh. So this is a technology that we do support. And hence, I will give you the good, the bad, and the ugly about Mesh. And in going with the theme of Hamlet, every slide in this presentation has a Hamlet quote or a slightly altered Hamlet quote. So, and it will try to match up with the message of the slides. So Oh God, I could be bound in a mesh network and count myself Emperor Wi-Fi of infinite bandwidth, were it not that I have bad dreams. So why does everybody like mesh? Mesh is actually something of a little bit of a miracle because it's giving me Wi-Fi without having to run those pesky wires. And what mesh does is that it provides Wi-Fi service to both clients as well as providing wireless backhaul eventually to some type of AP that's wired to your network. It will automatically calculate the optimal path through the network, and it will adapt to changes, which means if one of those nodes happens to go down or fall off the network or move away, mesh can manipulate, it can basically readapt and come up with the next best path to get back to the wired network. So, which makes it very robust because you could actually accept the failures of individual APs and still actually maintain your connectivity to more remote nodes without wires. It is designed for large-scale networks where wiring is impossible or cost-prohibitive. What a piece of work is mesh. How noble in reason, how infinite in faculties, in form and moving, how express and admirable in action, how like an angel in apprehension, how like a god, the beauty of no wire, the paragon of backhaul. Now, for those of you who, of course, know the original Hamlet, you'll know that Hamlet's soliloquy here, he was being very sarcastic, and so am I. So let's talk a little bit about terminology. You have what are known as root APs and node APs. So the root AP is a conventional access point with the AP with a wire connecting it to a wired switch to your infrastructure network. So this is typically a direct Ethernet connection or a fiber optic cable. It can also be, and this is very important, you can connect the root AP to a wireless point-to-point or point-to-multipoint bridge, because those wireless point-to-point and point-to-multipoint bridges acts like a wireless wire. So from the perspective of the mesh root AP, it thinks it has a wired connection, even if you're doing it over a point-to-point link on a separate channel. And that's really, really important when we get into how to actually design for mesh to be able to have that option in mind. You also have your node APs, which are your APs without a wired Ethernet connection. Now, you may have Ethernet running to a PoE injector for power, but they don't actually have an Ethernet connection back to your wired infrastructure. So in order to actually do the backhaul to the wired part of your network, it actually uses the wireless radio to establish a backhaul connection either to a root AP or if there are multiple hops to another node AP in the chain. Each wireless link for this backhaul is referred to as a hop. So you could have 1 hop, 2 hop, 3 hops. That's basically the number of wireless backhaul links that you're jumping from one AP to the next. Now, I always recommend using dual band APs because with a single band AP, you need simultaneous wireless backhaul and client access. Whereas with a dual band AP, I can use the 5 gigahertz band for wireless backhaul and client access, and I can devote my 2.4 radio only for client access. And when we get into the design, you'll see when I talk a little bit about the history of mesh, a lot of it started off with single band APs, and you can see why the technology literally didn't go very far. Neither a node AP nor a root AP be, for node oft loses both itself and friend, and root dulls the edge of client performance. I mentioned before that mesh will calculate the best path through the network and will adapt to changes in the environment, such as APs going offline. The algorithm is proprietary to every vendor, so every single vendor that supports mesh does it differently. Some of them do it wildly differently. The typical parameters, though, that you are generally optimizing includes things like minimizing the number of hops, because every hop is going to introduce latency and introduce a reduction in throughput. So you want to minimize the number of hops between your node AP and your root AP. You generally want to maximize the signal so that you can get the strongest RSSI and therefore the best MCS rates between neighboring node and root APs. And you may also want to balance the load across APs. So if you have a lot of clients on one AP, you may want to actually have another AP take a less quote-unquote optimal path in order basically to balance the load on what might be the stronger path, but an AP that AP might have a lot of clients connected to it, or it might have a lot of other remote node APs connected to it. So you may often want to balance the load to get improved overall performance. I should mention that these parameters, because it's an optimization problem, can actually conflict with one another. And this can often lead to counterintuitive and suboptimal solutions, which means that because I'm trying to optimize over multiple things, the solution that the network and the algorithms come up with, you might take a look at that as a network engineer and go, why the heck did it decide to route traffic that way? Because that makes absolutely no sense. But that's often what happens with these algorithms. There are more things in mesh optimization, Horatio, than are dreamt of in our philosophy. So of course, everybody always says that mesh lowers throughput, and there's a lot of stuff out there about whether mesh impacts throughput. So let me tell you kind of the story on mesh and throughput. With a conventional wired Wi-Fi network, you are dedicating all of your wireless airtime to client access. And all of your backhaul is going out over the wired Ethernet cable. So this is how a conventional Wi-Fi network operates. My radio is solely devoted to transmitting and receiving data back and forth between client devices, and all of my backhaul of all of that data for upload and download is going in and out over the Ethernet wire. In mesh, I'm utilizing that wireless airtime for both wireless backhaul and client access because I don't have that Ethernet cable. And as a result, I'm reducing both throughput and client capacity. And this is typically where the 50% per hop loss comes from, because if the AP is spending half of its time interacting with clients and half of its time interacting back and forth with the next node AP in the chain in order to get data back and forth to the main network, I'm literally losing 50% of my airtime per hop. The general rule, therefore, is to avoid mesh in performance-critical applications because of that reduction in capacity and throughput. You really should only use mesh in scenarios where running Ethernet cable is unfeasible. And by unfeasible, I mean it's either physically impossible or it's cost prohibitive. You should also only do it in environments where my performance is not critical. So I might need coverage, but I don't need a lot of coverage. I don't have a lot of devices in that space. So the fact that I'm losing some throughput is really not going to be a big deal. You cannot, sir, take from me anything that I will more willingly part with all, except my throughput, except my throughput, except my throughput.
Sorry, Jason, just to say, you're rock, man. You're playing rock.
Thank you. So let's talk about the ghost of mesh, self-interference. Mesh radios in a mesh group, or sometimes what we refer to as a cluster, where I have root APs and node APs. In order for them to communicate, just like an AP connecting to the client, they all have to be on the same channel. So every time an AP intercommunicates with the client device, that consumes airtime for neighboring APs as well. So basically, I have all of these neighboring APs, and they're all on the same channel so that they can communicate with each other. But if I'm also using those to talk to client devices, then every time I'm interacting with a client device, I'm further creating self-interference for the neighboring APs. And that's going to result in lower airtime capacity and higher retries. Now, many vendors will give you the option to solely devote the 5 gigahertz radio to backhaul only, as opposed to sharing that radio with both backhaul and client access. And that's what I usually recommend to people to get around this, because then I'm still getting losses per hop, but I'm not spending my time trying to communicate with client devices on that channel. And in deference to ghost frames, which were brought up at WLPC, I have incorporated the following quote from Hamlet. "I am the ghost frame, doomed for a certain period of time to propagate the earth at night, while during the day I'm trapped in the fires of purgatory until I've interfered with neighboring APs. If I weren't forbidden to tell you the secrets of RF physics, I could show you RF interference that would slice through your soul, freeze your blood, make your eyes jump out of their sockets, and your hair stand on end like dipole antennas. But mortals like you aren't allowed to see RF waves in the air. So let's talk about when mesh emerged in the early 2000s and why it failed. The original mesh APs, when they first came out, most of them were actually single band 802.11g access point. Later on, the more expensive versions were dual band, but they were dual band 802.11a and 802.11g, because so you had your maximum data, half duplex data rates of 54 megabits per second. And remember how mesh works. A mesh AP is going to spend half of its time talking to client devices and half of its time talking on the backhaul to the next mesh node in the hop. So that means that you're going to lose 50% of your throughput on the first hop. I'm going to lose another 50% on the second hop, so a total of 75%. Another 50% on the third hop, so 87.5%, and so forth. So when you had a maximum of 54 megabits half duplex data rate, which would typically give you a throughput, an actual kind of data throughput of around 20 megabits per second maximum, assuming you had kind of nice clean channels and were reasonably close by and high SNRs, quite honestly, it didn't take a lot of hops for, as Hamlet would say, the rest is silence, because your throughput would drop so low after 2, 3, 4 hops that the service became practically unusable. Now, for those of you who may be familiar with Hamlet, you'll know that there was a play that came out in the 1950s called Rosencrantz and Guildenstern Are Dead, which was took a look at 2 very minor characters in Hamlet and explored their story within the story of Hamlet. And I have taken this quote from the very end of that play. There must have been a moment at the beginning where our backhaul could have been wired. Somehow we missed it. Well, we'll know better next time. I should mention right after that line was said, Rosencrantz and Guildenstern were hanged. So, hence the tragedy. So if mesh was such a bad idea then, why is it such a hot topic now? Especially in the home Wi-Fi space. It turns out that the technology actually meets the need for home networks. Now, we've come a long way in the last 10 years, and we now have 802.11ac on the 5 gigahertz. And when you're deploying in a home, right, the 802.11ac throughput's usually much, much higher than the bandwidth that's actually coming into the house. So even if I have a 100 by 10 cable circuit coming into the house, right, with an 867 half duplex data rate, I've got some room to play. So if I'm losing 50% over a hop or two, I'm still generally okay. So we're generally more tolerant of those losses. Plus, the networks are small. So we're not talking about a lot of APs. In the 2000s, there was a big push for deploying entire cities and metropolitan downtown areas using mesh. Here, you're talking about 3 APs in a house. So it's very easy to install because I don't need to run cabling. All I have to do is plug it in. Many vendors have also made this even easier to configure by using Bluetooth and basically downloading an app to your phone and just configuring the APs off your phone. Many vendors sell this in the 3-pack. That's very common to see amongst multiple vendors. And typically you would configure this as 1 root node that's plugged into your cable modem and 2 mesh nodes that are elsewhere throughout the house. So you're really only talking about 1 hop and at maximum 2 hops in the area, because for a small coverage area like a private home, I don't have to worry about scalability. Mesh broke down in the 2000s because it didn't scale. And even though it supports higher speeds now, of course, our expectations for how much data we're pushing have also increased over the years. But in a small coverage area, right, I don't need to worry about scalability. The fact that I can only support 3 or 4 APs, yeah, that's actually fine. So though home mesh be madness, there is method in it. That said, the fundamentals are always fundamental. So when you do mesh, you are still sacrificing user capacity and data throughput. Your 5 gigahertz, of course, is going to attenuate faster through things like walls and people and furniture and so forth. So you may not always be able to get those MCS 9 rates. So you need to be very careful about how closely you place them. Generally, when you're meshing at 5 gigahertz, you got to place the APs closer together than you would at 2.4. The typical data throughput performance in reality turns out over a mesh network turns out to be roughly 25 megabits per second. It seems to be the general case. Some people get better, some people get worse. But what I've seen in several scenarios is typically if you run a speed test over a mesh network and you have, say, a 100 meg cable line coming in, you're typically really only going to get about 25 megabits per second. Now, that's perfectly adequate for many home applications. You can stream, high-def Netflix over that. You can't stream 4 or 5 of them over that. But you can still have very decent performance at 25 megabits per second. However, in demanding households, say you've got you've got 4 people streaming 4 different Netflix movies all at the same time, yeah, 25 megs is probably kind of pushing where you're going to go. Furthermore, right, you don't have any robustness built in for the flood of IoT devices that are coming on board, and all the smart home devices and Alexa and Google Home and everything else that's coming into our houses. So if you're already kind of borderline in terms of performance, even though each one of those individual devices doesn't take up a lot of bandwidth, as I start adding more and more devices, you're going to be adding more overhead to the network, more traffic on the network, and your mesh networks are just going to be less robust. So it's a little more than meh, but a little less than mesh. Now, one of the other funny things that happens in our industry is standardization, because there is this pipe dream out there that I'm going to have different vendors' mesh APs talk to each other. And it really is a pipe dream in order to enable inter-vendor communication. This was first envisioned back in 2006 with the IEEE 802.11s standard. And the Wi-Fi Alliance just this year put out an easy mesh certification to basically saying that, well, if all vendors are following this easy mesh specification, then you can mix and match APs from different vendors and still get them to talk over mesh to one another. Now, coming from the vendor community, I have no interest in supporting having my devices talk to other vendors' devices. I want you to use my devices. And every other vendor would basically tell you the same thing. Now, there are open source algorithms for doing mesh. One of the popular ones is called Batman, Better Approach to Mobile Ad Hoc Networking. There's also Hybrid Wireless Mesh Protocol, which was what the 802.11s standard was based on. There are a few others that are out there. Again, the reality, though, is that every vendor does mesh differently, right? The algorithm tuning, so what, remember I told you, right, on the optimization, I'm optimizing over different parameters. I've seen as low as 2. I've seen as high as about 100 different parameters that you can optimize over, and it really depends upon the vendor and how sophisticated they want to be in mesh and how much mesh is a part of their strategic marketing strategy. But every vendor does this differently, and it's usually considered a trade secret. So they're generally not going to tell you exactly what they're doing. And as a result, every vendor is using a different set of parameters to optimize. So the idea of being able to standardize mesh across different vendors, quite honestly, is a pipe dream. It's never going to actually happen in practice. This above all, to thy own nodes be true, and it must follow as the night the day, that canst not be false to any client. So I've been bashing mesh, of course, but sometimes, you do mesh because you have to, because I can't run wires, and it's the only way to get connectivity to certain areas. So, okay, when you have to deploy mesh, and I've certainly deployed mesh lots and lots of times, my advice to you is to do it right. So here's how you do it right. You want to cluster your mesh APs. And by cluster, I mean you're going to take a property, it's going to be all spread out. Your MDF is almost invariably going to be located in one corner of the property. Even if it's located in the center, that eases up things a little bit, but almost invariably, your MDF is often one corner of your property. And I'll show you an example of that in a few minutes of what that looks like. But you're going to want to cluster the mesh APs, which means that I'm going to basically space out my root APs to be roughly evenly spaced out throughout the property. So I'm going to define certain APs as being root APs, and I'm going to make sure I get wired or point-to-point wireless connections to them so that they can act as root APs. And then I want to ensure that I only have up to 4 remote nodes that are nominally 1 hop away from that root AP. So what this means is that at least 20% of your APs are going to be root APs. And all your 80% of your node APs are nominally 1 hop away from the root. Now, the reason that we do this is so that if that root goes down, those remote APs, which are now isolated in space, can then start looking around for another node AP to connect to. And even in a failure scenario, okay, now they're 2 or 3 hops away. But if you start with them being 2 or 3 hops away, then in a failure scenario of one of those routes, now they're going to be like 4 or 5 hops away, and the throughput is going to go straight to hell. Again, in order to create those routes, you're going to want to have dedicated wiring or separate wireless bridge point-to-point / point-to-multipoint backhaul links to create those additional root APs, and I'll show you an example of that momentarily. Now, when you do this, your backhaul channelization becomes extremely important. So you need to actually turn off auto channel on the root APs and on your backhaul links if you're using point-to-multipoint backhaul, and set them statically so that you maximize the amount of airtime that's available in the space, because I want neighboring clusters to be on independent channels. So that will maximize the airtime. If I only had 1 channel for everything, then I've got an entire property with multiple APs, and they're all on the same channel. And we're not running single channel architecture here, so that's going to be a major problem from a self-interference perspective. So when you do the channelization, you're going to set each of your root APs and each wireless bridge link to a static and non-overlapping channel, so that each mesh cluster is on a separate channel. You're then going to set all of your node APs to auto channel, and you do that because the node APs are going to be looking around and they're going to be scanning the channels to try to find the nearest root AP. They'll hopefully find the root AP that you've designated for them if you've laid it out closely enough, and they'll connect to the root AP that you want. If that root AP should happen to go down, then that node AP, you're not losing the entire cluster, you're just losing that 1 AP. And then those mesh APs, those node APs which are now cut off, are going to start scanning around, and they will find another node AP connected to another route, and now they'll be a couple of hops away. So these are the general guidelines for when you have to deploy mesh and you need to design a mesh network. These are the general guidelines that you want to follow. Mesh, the undiscovered country, from whose bourne no Wi-Fi engineer returns. So I'm going to show you an example of mesh in an RV park. The MDF, as I mentioned, is in a corner of the property. In this case, it's in the lower right corner. And all of the little bubbles that you see here on the Google Earth map are access points. The lines in red are point-to-point / point-to-multipoint links. And the colors basically represent those different mesh clusters that I was talking about. So for example, if you look in the lower left, if you look in the lower right corner of the screen, you'll see I've got this kind of green group, and then I've got this cyan group. Cyan group. And nominally, right, I have a point-to-point bridge link going from the green root node back to the MDF on the left side of the screen. I've got a second point-to-point link going from the cyan root back to the MDF. The other bubbles that you see with the lines there, those represent the mesh links. So you could see I've got 4 APs in each of those mesh clusters. Now let's say what would happen if that green AP that's labeled G8-R in this picture, let's say that AP goes down. So I'm in a corner of the property, and the one root node in that corner of the property goes offline for whatever reason. Those other 4 APs, the G8-1 to G8-4, are essentially cut off from the network, but what they will start doing is they will start looking around for other root and node APs. They'll probably connect to, say, G91, or maybe they'll connect to G62. So they'll have a few options based on what they can see. And so now I might be 2 hops or even 3 hops away from a root node that's got a wireless point-to-point backhaul link back to your MDF, but I still can provide service in that corner of the property. Even with that root node down, that service might be more limited, but I can still provide service. And in any type of failure scenario, slow is always better than off. So I'm always better off if I can provide slow service versus providing no service. And I'm showing here the APs that this design was done with for both the point-to-point backhaul links as well as for the mesh APs themselves. So this is easy, right? Maybe the Emperor Wi-Fi doth protest too much, methinks. So let me give you some takeaway messages. Mesh is only appropriate in very particular circumstances. You only do it when you absolutely cannot run wires. It should be your last, it really should be kind of your last choice of things to do. So I absolutely can't run a wire. And secondly, it has to be in an environment where the performance of your network just isn't critical, right? I'm not going to have, 100 people trying to stream 4K video over that mesh link, because I guarantee it won't work. But if it's an area where I don't have a lot of people and I don't really need a lot of bandwidth, mesh can work fine for that. Mesh involves compromises. So you're going to compromise both user capacity, because remember, if I'm going to devote my 5 gigahertz radio to backhaul, then I can't use that 5 gigahertz radio at all for clients. So I can only have clients connect on 2.4. If I decide I'm going to have it shared, then I'm going to be compromising. Again, I can handle less 5 gigahertz clients than I would otherwise, and I'm going to be compromising 50% throughput per hop. So anytime you use mesh, you are compromising the absolute capabilities of the AP. Again, in non-performance critical applications, you've got room to spare, and that might be a perfectly acceptable design solution. Designing for mesh is tricky, right? You got to group your nodes and your routes into these small clusters. You've got to carefully channelize your clusters, and you really should be dedicating one band, usually the 5 gigahertz band, solely to backhaul and not using that for client access, because you really want to decouple the radios that I'm using for client access to the network and the radios that I'm using for backhaul access to the network. So the mesh network is the thing to capture the conscience of Wi-Fi kings. Now, if you want to design for mesh with EKAHAU and with LigoWave, do you have a project that requires mesh networking? Come talk to us. You could come talk to me at LigoWave, or come talk to Jerry and UC at EKAHAU, and we'll get you squared away. Predictive modeling for mesh is the same as predictive modeling for any standard Wi-Fi network, where you're going to see the compromises on your 5 gigahertz, on your speed performance of those APs in terms of actual throughput. If you're walking around an existing mesh network site and you're taking an active site survey, again, the procedure is exactly the same as you would on an ordinary network, but where you will see the differences is in terms of the throughput performance. But if you have a project that requires mesh, come talk to me, come talk to my friends at EKAHAU. We can help you plan out your network with predictive design modeling and best practices to deploy in your environment. So get thee to a mesh network. And with that, I will leave it there, and I will open it up for questions. I hope everybody enjoyed my little Shakespearean take on mesh networking. And please ask away.
Well, certainly, sir.
I give you a little clap there. Can we ask for an encore? Is that acceptable?
Hmm?
Can we ask for an encore to the play here to continue it going?
We'll see what we can do. All right, but the encore might be Macbeth, so that starts getting a little dark. But sure.
Thank you so much, Jason. We have like a boatload of questions, and this Zoom webinar thing has a chat board as well, which opened up a whole new like back channel thing for this. Not anymore do you need to go to Twitter to also interact with us during the webinar.
Okay.
So that was kind of cool to follow, and you got tons of praise left and right. And there's a lot of questions on the official Q&A board as well. Jerry, you want to fire at will?
Yeah, we obviously this was a very popular topic. I was trying my best to keep up with the questions here, but yeah, I flagged a bunch of them here to bring up at the end here. So we'll try and get through as many of them as we can. And if you've got some questions, go ahead and get those submitted now, and we'll hammer through these over the next 15 minutes or so. So the first question here is around the talking about the nodes in like dual channel. Are they programmable? Is it possible to serve both the backhaul and the client access over 5 gigahertz?
So the answer is yes, and actually most, not all, but most vendors actually default to that mode. Usually if you want to devote the APs to solely 5 gigahertz backhaul only, you usually have to actually go in and make a configuration setting. That's the typical default that I've seen across multiple vendors. Again, though, when you are sharing 5 gigahertz access both with client devices and with backhaul to the next node, you are compromising both on the number of users that you can carry on that 5 gigahertz, and you are compromising throughput, because that will lead to your 50% per hop, throughput loss per hop. If you're devoting the 5 gigahertz network solely to backhaul, you're not losing that 50% per hop, because that radio never has to talk to clients. And your 2.4 gigahertz radio is only talking to clients. But obviously, if I only have the 2.4 radio talking to clients, then I'm losing client capacity. So either way, you need to make a compromise. And the question is, do I want to compromise on throughput, or do I want to compromise on client capacity, or do I want to compromise on both? And that really is up to the scenario that you're designing for. But when you're deploying mesh, you need to be aware of the fact that not having that wire there means that you got to give something up.
Excellent. Great answer.
Very cool. Did you talk through tri-band radios at any point?
So I haven't seen mesh implemented yet on a tri-band radio, because the tri-band radios are, typically they've got the 5 gigahertz low and the 5 gigahertz high. I have not seen a vendor actually introduce, I'm not saying that they're not out there, I've just not seen it. But in theory, you could use the 5 gigahertz high, for instance, for doing your mesh backhaul, and the 5 gigahertz low for servicing clients. So yes, with a radio, and there were, I didn't mention this in the presentation, but I know towards the end of the metropolitan mesh days in the 2000s, there were vendors coming out with like 3 radio and 4 radio APs that were 802.11a and 802.11g, and the idea being that those radios would be solely, that some of those radios would be solely devoted to backhaul in order to get around this 50% throughput limitation. So again, though, if you're using a tri-band radio, right, you're going to wind up compromising quite a bit on what channels. It's going to make channelization even harder, because you're going to get limited to what channels you can use for mesh and what channels you can use for client access. So you're basically leaving yourself 1 to 2 channels on each of those radios. And that can make channelization very difficult if it's a larger project and you're doing multiple clusters. So you would really want, a multi-band, I won't use the word tri-band, a multi-band radio where that third band is actually really something different. Maybe 3.5 gigahertz, maybe 60 gigahertz. And again, though, designing for all of that has its own limitations and its own bandwidth and so forth.
Yeah, it's kind of a catch-22, right? Because if you're deploying mesh, that means you're using multiple radios in the environment, as it stands. That's the whole point of kind of mesh. So you're shooting yourself on the spectrum side of things, and not being able to reuse those channels.
Quite honestly, when I run into networks like this, what I'll often recommend is actually doing point to multi-point backhaul to every single AP. And then it becomes a point to multi-point design challenge. But where you're not using mesh, but all of your wired backhaul is actually wireless over a network of point to multi-point APs that are presumably on separate channels.
Hey, Jason, there were a lot of questions. I'm sorry to bring this to a sales pitch again, but there were a lot of questions regarding, how to do this in EKAHAU and stuff like that. You mind if I just steal the presenter rights for a second?
Please do. By all
to
means.
Illustrate, I am sorry for kicking you out. So, just to illustrate how, for example, you could do mesh planning, I have a predictive file here of let's say, a fairly typical maybe residential area where we have semi-high-rise buildings, like 1 floor, 2 floor, up to 5 or 6 floor. So we have defined those buildings as attenuation areas of different height. You can see here most of the buildings are 15 meters, whatever, and they have a high attenuation value. So you do that by, of course, just doing free-form attenuation areas, where you then put in the height of the buildings and stuff like that. And there's ready-made materials like these whole map things, foliage, building, things like that. So I have defined some foliage here at 2 dB per meter, and then there's other stuff. Anyway, my point is, now we're looking at how these APs bolted onto the sides or tops of these buildings work. For example, on 5 gigahertz or 2.4. And this is at the client receiver height, right? But for mesh, I'm sure Jason and Jerry know better than I do, but I would imagine for mesh, it's often like from building to building, for example. So how do we visualize if this AP that's set at 17 meters height, how does it work at a height of 15 meters? Because we want to see where are the good locations at the rooftops, for example, to do the next mesh hub. And and this is where the hidden feature that I showed you earlier comes in. So if you hold down the control key, then click options. Here's a new selection here saying visualization height. And if I want to understand how it looks like on those 15-meter rooftop buildings, or what would that be, feet, 45 feet rooftops, I would put here, visualize that for me at 15 meters height, press enter. And now we're seeing what those APs coverage looks like at the rooftops of most of these buildings. So again, control click on the options and visualization height. And then when we want to go back, of course, to the client perspective, we would take 1 meter by default. Or if you want to visualize how it would look like for the subscribers on the 2nd floor of the building, I could put, let's say, 5 meters here. How does it look like for, all the subscribers that need client connectivity on the 2nd floor of these buildings? That's how it would look like. So don't be fooled by the 2-dimensional user interface. It's fully 3D, and you can do a lot of neat things with it, including some mesh planning. And as I was asking on the chat board as well, if you'd like more mesh optimized features to ESS, let us know. First of all, would you need them? How often would you need them? What kind of features they should be? And would you be willing to pay extra for them? Anyway, back to questions.
By the way, you see, that's a really cool feature. That is a really cool and very useful feature for deployments like this, especially when the mesh APs, because you would typically put mesh APs on a rooftop or 15 feet, 5 meters up in an RV park or something, right, to keep them out, so being able to know how the APs are seeing each other, is one viewpoint versus how the clients are seeing the APs. Definitely makes a huge difference.
Exactly.
All
Jerry,
right, next question. Next question here is, why do the mesh APs need to be on the same channel for both, especially for talking like doing this, backhaul and serving clients? Why does that need to be on the same channel to make that work?
Well, because, I mean, otherwise how are the radios going to talk to each other, right? So, I mean, this is standard. At the end of the day, in standard Wi-Fi, right, both your transmitter and receiver have to be on the same channel in order to hear each other. And you could think of nodes as being client devices for the routes, is one way of thinking about it. But at the end of the day, right, if I have any transmitter versus any receiver, they have to be on the same channel in order to talk to each other. And if I want all of my mesh APs to see each other, then they all have to be on the same channel. That's just how Wi-Fi works.
Okay.
So this is why I generally recommend kind of breaking them up into clusters, because then I could put the clusters on different channels, and then I have more airtime that I can take advantage of. Right. Yep. So within the cluster, they're all on the same channel, but between neighboring clusters, I can basically create a barrier between the clusters in terms of airtime utilization.
So essentially, that root AP would define what channel that cluster is going to be on, right? Am I understanding
that's correct. And then if that root AP goes down, because the mesh APs, the node APs are on auto channel, you know, as soon as they lose their connection, they're usually going to start searching for, right, the next best path, which will guide them to another root AP. So yes, you would set your root APs on a static channel, and you would set your node APs on auto channel.
Excellent. All right, so next question we've got here is around antennas for mesh deployments, you know, indoor, outdoor, omni versus directional antenna. Do you have any kind of recommendations around antennas for deploying a mesh network?
So typically most people do omni because you want to be able to see everything in the space. If you're at the corner of a property, I would obviously do a sector antenna or something like that, because I don't need any coverage right outside of the property that I'm covering. You could use directional antennas on the APs, but, you know, keeping in mind though that if you're also using that band for client access, it's the same set of antennas for both talking to neighboring APs and talking to client devices. So, you know, so for the example that UC just showed, if I design my antennas to optimally talk to neighboring APs, chances are I'm suboptimally talking to my client devices that are at a different level. Generally, it's actually the opposite is what actually happens in practice, which is I'm picking omnidirectional antennas in order to be able to speak to the client's devices. That could be anywhere, you know, in a 360-degree field of view around me. And I mean, I need to use those same antennas to talk via, you know, mesh backhaul back to the network. Again, this is another reason why mesh is essentially a coupled design, because I'm coupling the functionality of client access to the functionality of backhaul. So unless you're taking a radio and you're devoting it solely to backhaul, right, then I'm going to need to make compromises on the antenna, because I really have to worry about my coverage needs for both client devices and for mesh backhaul. So if you really want to separate them out, right, one of the things that I like to do is skip mesh and do the backhaul via point-to-point, because now I have truly uncoupled the wireless access to clients to the access back to the main, you know, the backhaul access to the main network. But that, of course, means I'm adding an extra radio and I'm adding extra parts, and it costs me more, and so forth. But it's a great question.
Yeah, and I feel like this one kind of goes along with that about the antennas, or I'm curious to see if it will. Is there a trick to getting nodes to associate with a single root AP? Specifically, giving an example, we've had issues where nodes connect to the wrong root AP despite configuring a preferred route. I'm wondering, like, from an antenna standpoint, is there maybe a solution there, a recommendation to help with that?
You could. I mean, you know, again, every vendor's algorithm works differently, but typically they're trying to, you know, I mean, universally, most vendors are trying to balance the, you know, maximize the SNR, right? So maximize the RSSI between one hop and the next, and they're trying to minimize the total number of hops. They may be optimizing other parameters as well. I worked with a vendor years ago that specialized in metropolitan mesh. I won't mention who it is. It's not LigoWave, it was somebody else. And they told me, their engineers told me they optimize over nearly 100 different parameters, in addition to the 2 main ones that I mentioned. They had it down to an art form. But as a result, you could wind up with these wacky solutions. And you're looking at it as an outsider going, why is that AP connecting to that node? Because it all comes down to, not, at the end of the day, if it's going to pick the network that's got the strongest signal and the minimum number of hops back to a route, usually. But if you have a vendor that's optimizing over more parameters, or who has a flawed mesh algorithm in one way or another, you could get some very wacky results that are very non-intuitive. If you really want to kind of lock it in, then you would actually set and I have done this in a couple of cases, you actually set the node APs to the same channel as your desired root AP, because then it will only see its own cluster. Now, the risk in doing that, of course, is that if the root goes down, those node APs are still stuck on that one channel, and there ain't nothing else around it on that channel, and now you're really stuck, because now, in addition to losing that root, you've lost the whole cluster. But if you really want to lock in this mesh AP, this node AP is connecting to this root AP, then you statically assign the channels on both of them to be the same.
Okay. Jerry, what do you think? We are 1 minute past the hour. One final question.
Yeah, did you have one on deck? I know we've got a lot of questions here that we haven't gotten to.
Yeah, there's so many good ones to choose from. Hey, did we talk in depth about when to use 2.4 and when 5 for the backhaul? Maybe you covered this, but I was tuned out reading.
So there are vendors. Actually, it's a good question because there are vendors who will actually give you the option of saying use the 2.4 gigahertz for backhaul versus using the 5 gigahertz for backhaul. You can use 2.4 gigahertz for backhaul. Obviously, you have lower total spectrum available, so your bandwidth is going to be lower. So that's one issue with using 2.4. The other issue with using 2.4 is remember what you're doing. At the end of the day, you want clients to get online, and I still have a ton of single band clients out there. Even some of the lower end smartphones that you could buy today are still 2.4 only, and all of those IoT devices are 2.4 only. So if you say, okay, I'm going to use 2.4 for backhaul and I'm going to use 5 gigahertz for client access, I've basically eliminated the ability to connect 2.4 clients. So, and even if you're saying, okay, I'm going to use the 2.4 radio for talking to clients and talking backhaul, you're now just slowing down your network even further. So many vendors will let you do it. I would typically, there might be a scenario where it makes sense, but I have not encountered it.
One thing that comes to mind with regards to that is maybe if you have a lot of foliage in the way and stuff like that, that's when the connection is kind of flaky on 5 gigahertz and weather, rain on the leaves, snow on the leaves might make it even flakier. If you just can't for sure penetrate all those obstacles on 5, then
you might break through on 2.4. Yeah, so that might be a scenario where you might want to consider doing that. You might also want to consider using a chainsaw and cutting down some branches to improve line of sight.
All right. Yeah. So, I like that. That's a topic for another webinar, right?
Yes. Right. Well, that gets into our Macbeth discussion. So, I did see one. I know we're over time. I did see one question here that looks really interesting about ODFMA. Because
yes, sir.
802.11ax.
Oh, I'm hearing AX is dead already in my ears from you, man.
Yes, somebody got up in October and actually publicly said that at the CWNP conference.
I remember that.
We won't say who. But despite the fact that I believe it, right, those products are going to be out there. And so what ODFMA will, I haven't really thought about this. It's an excellent question. But what ODFMA is going to allow you to do is basically break your channel into subchannels. So in essence, it essentially would give you an additional radio because, right, if I'm saying, okay, I'm going to take an 80 megahertz channel and I'm going to devote, say, 40 megahertz towards backhaul and the other 40 megahertz to talking to clients, you know, I've essentially added a third radio in there. So that would definitely help from the throughput standpoint. You know, obviously, though, I can't use the full 80 megahertz for backhaul, so I'm limiting the, right, ODFMA is not going to increase speed in this case, right? So, because I'm now using a 40 megahertz channel for backhaul as opposed to an 80 megahertz channel for backhaul. So you're already compromising on speed based on the fact that I'm using smaller channels. But it might be a scenario that works for mesh to use ODFMA to do that. That's entirely possible. Again, though, you're still compromising on throughput because I got to use smaller channels. So you're compromising on throughput that way. However you do it, right? However you slice it, however fancy we make the technology, the fundamentals are still fundamental. So somewhere I got to make a compromise. Obviously, some compromises are going to be better than others, right? And for particular scenarios, some compromises might make more sense than others. And that's fine if that meets your requirements.
The fundamentals are still fundamentals. Dude, you bring the fun to fundamentals. What can I say? So, thank you so much, Jason, for joining. Thank you so much, Jerry. Thank you so much to all the listeners. Let's keep the conversation going. For example, on Twitter, of course, we will send a follow-up email and all that kind of stuff. But the feedback has already been overwhelmingly positive. We do apologize for not answering all the questions. We've run out of time, but let's keep the conversation going. You will find us on Twitter as well as on LinkedIn. So
yeah, anybody who has questions on this stuff, please feel free to tag me at Emperor Wi-Fi, and I'd be happy to you know, try to answer those questions on Twitter and over the course of time as people ask them. So, you know, if you have questions on mesh and how to use it, please feel free to ask me and ask other members of the community, because we are a resource for you in order to answer these questions. And if you're not on Twitter, get on Twitter, because that's where all the Wi-Fi engineers hang out, and we're all very friendly, and we may not always agree, but we're always willing to help.
We're all friendly. I wouldn't go that far, but
well, usually.
All right. Thank you so much. And if you can't go to Twitter for whatever reason or don't want to, you'll find us on LinkedIn. So, you know, first name, last name on the search there, and hit us up, connect, and let's continue discussions.
Okay. Well, thank you, Jussi, for having me. It's been an honor and a pleasure.
It's our pleasure, man. I hope to do this again. We still haven't done that small medium business webinar, so let's shoot for that, right, Jason?
Absolutely. We will definitely talk about doing a follow-up on small medium business design.
All right.
Absolutely.
And Jerry, thank you for setting up the Zoom system. I think it worked pretty flawlessly, huh?
Yeah, we'll see. I'll keep an eye out for feedback on it, but on my end, everything sounded good, looked good. So yeah, hopefully this is a good solution going forward for our audience.
Awesome. Thank you so much, everybody. With that, have a great evening. Jerry,
thank you, Jussi.
Thank you, Jason.
Thank you,
everybody. Thank you, Jerry.
Thanks, Jason.
Jerry, I guess the recording is automatically saved to the cloud.